Okay, looking at the problems for chapter 22, we have just two problems here. The first one is broken down a few pieces just to make sure you go about it the right way. The second one is just a straight equation. Let's do the second one first, just because we can get that out of the way in no time flat. So the second one says an electric motor is made using a permanent magnet with a magnetic field strength of 0.0533 Teslas and a circular loop with a radius of 2.54 centimeters and 275 loops. Assuming a split armature, that means that we have the pads on that armature, and our connectors are these little brushes, as we call them. So this is connected to a power supply, which in this case is probably going to be a DC power supply. Since it's a split armature, you don't want split armature with AC. So it's going to change. This pad will be on this side for a while and then that side for a while. Okay, so assuming a split armature, find the peak torque created by this electric motor if a consistent current of 2.55 amps flows through the coil. Now, what we learned when we talked about this in class was we have the loop here, and we have a magnetic field, and the torque we have through that loop turned out to be INBA. And then honestly, I don't remember if it was sine or cosine, because it depends on how you align things. Sine of theta, where theta is the angle between the normal to the loop and the magnetic field. So when the normal to the loop and the magnetic field are aligned the same direction, then the torque is zero. And then as this thing rotates, you're going to have changing torque. So it asks for the maximum. Well, it's very easy to tell where the maximum is going to be from this equation, because all of these things are going to be constant. And so sine theta varies between -1 and 1. So the torque is going to be maximum when sine theta is 1. So torque max is going to be INBA. And so just putting in our numbers, that's going to be the current of 2.55 amperes times the number of loops, 275 loops, times the magnetic field strength, which is 0.0533 Teslas, and finally times the area, which is pi times the radius squared. So put all those numbers in, and of course I just realized that when I did my solution, I did not do it right. I just multiplied all the numbers instead of realizing that I have to multiply by area. So it's going to be equal to, and let me just do this real quick on my spreadsheet. And I have 0.0758. Make that bigger so I can read it. Newtons times meters. Okay, so that was not a synthesis problem. That was an application problem. Now this next one would fall into the synthesis category, the number 1. So number 1, a mass spectrometer is made by accelerating singly ionized, that means missing one electron, molecules initially at rest through a voltage difference of 1,000 volts. The molecules are then injected into a region with a uniform magnetic field of 4.25 Teslas. And I didn't specify, but that magnetic field is perpendicular to the velocity. What is the mass of a molecule if it does a semicircle in the spectrometer with a radius of 5.35 centimeters? So let's draw that figure first. So I start, notice it's missing one electron. So these are going to have a positive charge. So here's my initial charge, and I have, let's say, minus 1000 volts and 0 volts. So it's going to go through a voltage difference of 1000 volts. Actually, did that the wrong way. Start at 1000 and go to 0 because it's positive. So positive goes to lower voltage. And so this particle is going to have a force. The electric field is going like this, of course. And so the force is equal to QE. And that gives us the change in potential energy is equal to the force times the distance. So QE times the separation. But the electric field, if we have a uniform electric field between two parallel plates, the electric field is the voltage difference over the separation. So this is equal to Q delta V. So the change in potential energy is Q delta V. Now, in terms of signs, the change in potential energy is going to be negative because it's going to a lower potential energy going to a lower voltage. So notice delta V, the final is 0, the initial is 1000, Q is positive. So in fact, my change in potential energy is going to be equal to 1E times minus 1000 volts equals minus 1000 electron volts. Where's that energy go? That energy is going into kinetic energy. Using the work energy relation, I have work net is equal to the change in kinetic energy, and the work net, plus change in potential energy. Yeah, I did that. It was right the first time. Work net is change in kinetic energy. Its work non-conservative is equal to change in kinetic energy plus change in potential energy. These two are exactly equivalent because work net is equal to work non-conservative plus work conservative. But work conservative, by definition, is minus the change in potential energy. So work non-conservative, that is the work done by things like friction, which is equal to 0 in this case, is change in kinetic energy plus change in potential energy. So that gives me the change in kinetic energy is minus the change in potential energy minus Q delta V. So the first step is find the speed. So kinetic energy is 1/2 mass times speed squared. It told us it started from rest. Actually, did it tell us it starts from rest? It should have. Initially at rest, yes. So V initial was 0. So change in kinetic energy is 1/2 mass times speed final squared minus 1/2 mass times speed initial squared. Well, speed initial is just 0. So putting this in for change in kinetic energy, I have 1/2 mass speed final squared equals minus Q delta V. Therefore, and believe it or not, I have to look back up here because I don't have this open at the moment. The equation for speed then is going to be speed final is equal to the square root, multiply both sides by 2, divide them by m. So those cancel. And so it's minus Q delta V times 2 over m. Now keep in mind that minus sign is real. It's there. But delta V is also negative, so that's the square root of a positive value. So that's our answer for the first one. V is the square root of minus 2Q delta V all over, I think that's all over M. Yep. Now, when moving in a magnetic field, we can use Planck's law to determine that the radius of the circular path is as a function of speed, charge, mass, and magnetic field strength. And is given by, I'm sure my grammar here is not perfect, by the equation R equals. Well, the law I'm going to use is going way back in time. Newton's second law. So let's continue on. What's going to happen? And suddenly we're in a region, a uniform magnetic field. Now this has a positive charge. Remember, force magnetic is equal to QV cross B. So I have my V is going to the right. In this picture I drew B going down, so using my right hand rule, I put my index finger so it's pointing to the right, orient my hand so my middle finger points down into my screen and my thumb points up. So the force is going to be like that. And so that's going to cause, that force is perpendicular to my velocity. It's going to remain perpendicular to velocity, and it's going to make it do a semicircle like this with some radius r, which was given in the problem. So the law that I said I'm going to use is Newton's second law. Sum of the forces in the central direction is equal to mass times acceleration central direction. Looking at my diagram, the sum of the forces going toward the center is QVB. Now remember, this was a cross product, so the magnitude is Q times V times B times sine of the angle between V and B. V and B are perpendicular, so the sine of 90 degrees is 1. So that's why it's QVB for the magnitude equals M. And centripetal acceleration is V squared over R. So I'm supposed to take this and I'm supposed to solve this for R. So just solving this for R, I have R is equal to mv squared over qvb. Cancel what I can. Equals m. Oops, that was a square. Mistake. This was squared, so when I cancel, I only cancel one of them. So my radius is mv over qb. So I have there an equation for the speed as a function of the mass. Here I have the radius, a function of the mass and the speed. So I'm going to combine these two. So I'm going to combine this here with this here and run out of space. So if I want to solve for m, the first thing I'm going to do is put this v equation in. So I'm going to have that. Now I want to solve this in the end for mass. Well, actually, it says inserting the equation for speed from part A into the equation for mass in part B, we find that the equation for radius is, so that's my equation for radius. Now I can simplify a little bit. Equals square root of minus 2m delta v over qb squared. Note when I brought the m inside, that became an m squared inside. And when I brought the qb inside, of course, it became a q squared b squared. And then canceling, 1m canceled, 1q canceled, And I was left with minus 2m delta v on top and qb squared on bottom. So that's r is equal to, I already forgot, square root of minus 2m delta v over qb squared. Now I want to take that and I want to solve it for mass. And so if I solve that for mass, I'm going to first square both sides. So I have r squared is equal to minus 2m delta v over qb squared. And then solve it for mass by simply multiplying everything by qb squared over minus 2 delta v. Which gives me mass is equal to qb squared r squared over minus 2 delta v. And then I just have to put numbers in. So putting in numbers, that's going to be, oh boy, I don't have room here. I'm going to have to go back to the previous page. Mass equals, I'll bring the minus on top. Qb squared r squared over 2 delta v. So that's going to be equal to minus 1.602 times 10 to the minus 19 coulombs. My magnetic field for this problem was 4.25 Teslas squared. My radius here was 0.0535 meters squared. All over 2 times my change in voltage, which was minus 1,000 volts. So when I put that in my calculator, and I did this twice, but 2 different methods from this, so I'm going to do it a third time now, equals Q times B squared times R squared divided by 2B. Get all the signs straight. And good. I still get the same answer. 4.14. I only have 3 significant digits, so I'm just going to stop there. Times 10 to the minus 24 kilograms. That's the first of the answers here. 4.14 times 10 to the minus 24. But I asked for it in atomic mass units. That's what U stands for, is atomic mass units. So I have to use my conversion factor that 1 atomic mass unit is equal to, and where did I put that number here? 1 atomic mass unit is equal to 1.660539 times 10 to the minus 27 kilograms. So mass is equal to 4.14 times 10 to the minus 24 kilograms times 1 atomic mass unit over 1.660539 times 10 to the minus 27 kilograms. And that's equal to 249 atomic mass units. All right, so there's 2 problems involving magnetic force, and hopefully that has you more ready for the test.